Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. In a recent Space News, Thunderblog contributor Jimmy Micketts offered a thought-provoking analysis of an audible phenomenon that has puzzled scientists and laypersons alike for decades: the mysterious so-called hum. As we've described in many episodes, anecdotal accounts dating back centuries describe puzzling sounds associated with electromagnetic phenomena, such as the Northern Lights. But what about the ability of sound to produce in matter phenomena that may be fundamentally electrical? So-called sonoluminescence, or the emission of light flashes when sound waves passing through liquid burst bubbles of gas, is a source of both puzzlement and growing scientific interest. An article in the journal Nature entitled "Collapsing Bubbles Have Hot Plasma Core" describes detailed measurements of the phenomenon. It states, "They call it a star in a jar. When sound waves crush bubbles of gas in a liquid, energy is released in a dramatic burst of heat and light. Now the first detailed measurements of the phenomenon have shown that the molecules in the gas really do create a pinpoint of plasma, the energetic soup of ions and electrons found in every star." The research raises hopes that the effect, called sonoluminescence, might one day be used as an almost limitless source of energy. In this episode, Jimmy Micketts explores the possible importance of sonoluminescence in our electric universe.
What if sound didn't only flow through matter but could produce unexpected phenomena like light? Research in sound has revealed the capacity of sound to influence matter in a way that produces light. The phenomenon of sonoluminescence is one example of this relationship. Sonoluminescence occurs when high-frequency sound vibrates tiny gas bubbles to reach star-like temperatures and emit flashes of light. The mechanism of sonoluminescence is not fully understood, but its occurrence is well documented. As SL researchers probe deeper into the phenomenon, they have found that current fluid dynamics equations do not explain why it happens. Sonoluminescence is a natural phenomenon as well, and marine biologists observe some species of shrimp using it as an attack against other creatures. It is the bridge between sound and light and can offer a deeper understanding of nature's laws. In a study at UCLA called Sonoluminescence: How Bubbles Turn Sound into Light, scientists S.J. Putterman and K.R. Wenninger explore the mathematics and phenomenology of sonoluminescence. It is known that this phenomenon is caused by the rapid expansion and contraction of a bubble. This is known because the broadband UV light emitted appears at a frequency, though not continuously. Think of a strobe light as an analogy where flashes of light last only picoseconds, which is a trillionth of a second. According to Professor Putterman, the phenomenon of sonoluminescence can heat bubbles up to tens of thousands of degrees. The surface of these bubbles burn at 20,000 Kelvin, which is 35,000 degrees Fahrenheit, and they look like little stars. Quote, "Sonoluminescence, the transduction of sound into light, is a phenomenon that pushes fluid dynamics beyond its limit. Sonoluminescence can be repeatedly produced in a controlled laboratory environment. Some of the key requirements are degassed water, a noble gas mixture bubble, and a source of high-frequency sound. Typically, the sound is produced by a piezoelectric element. The scale of the experiment is typically small. Only about a cupful of water is necessary, and the size of the bubble is typically only microns in size. It should be obvious why the phenomenon has gotten the nickname of star in a jar. The small cavitating bubble takes on the appearance of a small star. Conventional fluid dynamic equations do not account for sonoluminescence entirely. Specifically, some research have applied Raleigh's equations to the bubble collapse, but this, quote, violates its domain of applicability according to Putterman and Wenninger. This violation occurs because Raleigh's equation is only for low Mach number motion, and the bubble collapse occurs at a high Mach number. Putterman and Wenninger also suggest that researchers misapply Saha's equation and Bremsstrahlung equations to this phenomena. Without getting too deep into the details of these equations, Saha's equation typically describes an ionization state of a gas relative to its temperature and pressure. Similarly, Bremsstrahlung equations typically describe electromagnetic radiation produced by the deceleration of a charged particle. At present, these equations do not adequately explain sonoluminescence for a variety of reasons. Some researchers believe that during sonoluminescence, bubbles have an inner core of plasma. In a study published in peer-reviewed journal Nature entitled Plasma Formation and Temperature Measurement During Single Bubble Cavitation, researchers state that, quote, emitting species must originate from collisions with high-energy electrons, ions, or particles from a hot plasma core. Other research supports the hypothesis that sonoluminescence bubbles have a hot plasma core. According to another recent publication called Evidence for a Plasma Core During Multi-Bubble Sonoluminescence in Sulfuric Acid, the observation of molecular and atomic ions is the first experimental demonstration of an inner ionized plasma core during single bubble cavitation. Thus, current research suggests that the core of the sonoluminescence bubbles may be plasma, the fourth fundamental state of matter. Perhaps this is the reason why fluid dynamic equations do not match the phenomenon. Researchers discovered that during sonoluminescence, a bubble rapidly expands, then contracts in cavitation. Looking deeper into this, researchers have found that the bubble does not operate within some conventional chemical laws. One of these is the fact that, as the bubble collapses, it rebounds because of van der Waals forces. The accompanying graph depicts a collapse of a cavitating bubble over time. Notice that the bubble has a peak radius of about 5.3 micrometers. The bubble then rapidly collapses at about 20 nanoseconds. As the bubble, quote, bottoms out, approaches the van der Waals radius, it springs back and oscillates through several cycles of expansion and contraction. Sonoluminescence appears to emit the most light with noble gases or noble gas mixtures. This is probably because of the inherent non-reactivity of the noble gas chemical group. Researchers use helium, neon, argon, and xenon to create sonoluminescence. Star-in-a-jar researchers use oxygen and nitrogen mixed with noble gas to create sonoluminescence in a laboratory. According to Putterman and Wenninger, sonoluminescence with only oxygen and nitrogen is difficult. A nitrogen and oxygen mixture produces a dim light. The article also states that noble gases concentrate in the bubble as cavitation occurs. This happens because the force of the bubble collapse causes reactive elements like H2O, N2, and O2 to dissociate. Then, the surrounding water draws these gases into it. An incredible example of sonoluminescence is the stun action of both the pistol and mantis shrimp. These predatory shrimp knock out their prey by loading their claws with tension and releasing it suddenly. The shrimp clamps its claws shut at such an extreme velocity that the surrounding water vaporizes. As in the laboratory form of sonoluminescence, this extreme cavitation produces the same light and extreme surface temperatures. However, this light is not visible to the naked eye as in the laboratory experiment. Researchers Detlev Lotz, Barbara Schmitz, and Michael Versluis have named this, quote, shrimpoluminescence. An article published in Nature regarding the topic called, quote, snapping shrimp make flashing bubbles states plainly that SL occurs at the snap. It is not obvious why a bubble created by high-frequency sound contained in nothing more than a glass of water could reach temperatures close to the surface of the sun. Not surprisingly, researchers first looked at fluid dynamics to reach an explanation for sonoluminescence but found it lacking. Could plasma physics be the road by which an explanation will arrive? Will the electric universe model explain what is happening? As more research unfolds, a deeper understanding of the nature of this bridge between sound and light could lead to both greater scientific understanding and practical applications.